Recording. Atomic structure 4. Electrons and atoms and ionization energy evidence. The essential idea here is the quantized nature of energy transitions is related to the energy states of electrons in atoms and molecules. Nature of science. There's experimental evidence to support theories. In this case, emission spectra provides evidence for the existence of energy levels. Let's have a look at this electromagnetic spectrum, a bit of a recap. Wavelength is inversely proportional to energy and frequency. We can see also that energy is directly proportional to frequency. If energy increases this way, well then wavelength gets shorter because they're inversely proportional. Frequency, however, is directly proportional. So as energy increases this way, so frequency also increases that way. And remember that you need to know the wavelengths for violet and for red in the visible light part of the electromagnetic spectrum. Right, we're going to do a bit of math because we all love math. Energy is directly proportional to frequency. You can see here, energy and frequency directly proportional. And there's some kind of strange H between there. Energy, we measure in joules. H is Planck's constant, and that's joules times seconds. And frequency is measured in seconds to the minus 1 over seconds, or hertz. You'll notice there's a fancy V there as well. This is the Greek symbol for nu, and I think that's the 13th letter of the Greek alphabet. Let's do a quick example. Calculate the energy in kilojoules of a photon of ultraviolet light with a frequency of 4.5 times 10 to the 16 seconds to the minus 1. Right, so write your formula, and we know Planck's constant 6.63 times 10 to the minus 34 joules multiplied by the frequency given in the question, and you get 3 times 10 to the minus 17 joules. But we want it in kilojoules, so we divide by 1000 to get to kilojoules. Now, frequency is inversely proportional to wavelength. Let's have a look at here. Frequency is inversely proportional to wavelength. And we've got this C sitting up there. So I wonder what that could be. It's the speed of light, and it's roughly 3 times 10 to the 8 meters per second. Wavelength, the symbol is lambda, measure that in meters, and F, or fancy V, equals frequency, seconds to the minus 1 over seconds, or hertz. Let's try one. Calculate the wavelength in nanometers of a photon with a frequency of 2.6 times 10 to the 14 seconds to the minus 1. So, speed of light equals frequency times wavelength. So wavelength equals speed of light over frequency. And there we have it. Speed of light divided by the frequency gives us 4.83 times 10 to the minus 7. This is in meters. We want it in nanometers, so we use the conversion factor. There is 10 to the minus 9 meters for every 1 nanometer. So we get 483 nanometers. This formula here can be found in table 1 of the data booklet. Let's try another one. Energy is inversely proportional to wavelength. So we know energy equals HF, Planck's constant multiplied by frequency. And we know that HF equals, we know the frequency equals the speed of light over wavelength. So we know the Planck's constant multiplied by the speed of light over wavelength gives us energy. Let's do an example. Calculate the energy in joules of a photon with a wavelength of 410 nanometers. So use this formula, we plug in. We've got Planck's constant multiplied by the speed of light divided by 410 nanometers. But we need to change this into meters. So we use the conversion factor. 1 meter is equal to 10 to the 9 nanometers. And that gives us our answer in joules. Ionization energy. The ionization energy is the energy used to completely remove an electron from an atom. So for example, one gaseous atom of a metal will give us one gaseous ion of that metal and an electron. The precise definition for ionization energy is: ionization energy is the energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous state. You should make a flashcard with this in it and carry it around until you can say it backwards. The units for ionization energy are kilojoules per mole. Energy levels in an atom converge at the high levels. You can see them getting closer together as they get higher. A continuum occurs at the convergence limit up here. It's drawn as a dotted line there. Electrons can have any energy beyond this continuum. Therefore, electrons are basically free from the atom once they get beyond here. They no longer have discrete energy levels. So, they have specific discrete energy levels within the atom, and then they are outside of the atom when this is no longer the case. Ionization has occurred when an electron moves from n equals 1 to n equals infinity. Here we can see ionization energy represented by the Lyman series. Remember, the Lyman series was the emissions where an electron falls back down to the ground state, to n equals 1. And these are seen in the UV region of the electromagnetic radiation spectrum. The frequency of light emitted at the convergence limit in the Lyman series can be used to find the first ionization energy. The emission with the highest frequency or energy in the Lyman series represents the energy emitted when an electron falls from n equals infinity all the way back down to the ground state, to n equals 1. Let's have a look at an example. Calculate the first ionization energy for the hydrogen atom in kilojoules per mole, given that the line with the shortest wavelength in the Lyman series is 91.6 nanometers. The shortest wavelength in the Lyman series is the highest energy, and that is n equals infinity, all the way down to the ground state, n equals 1. So let's find the energy released for one electron first, and then we can find the energy released for 1 mole of electrons. Energy equals Planck's constant multiplied by the speed of light divided by wavelength. We put the numbers in and we get how many joules are released when it goes from the convergence point to the ground state. Now we need to find how many for 1 mole of electrons. So we use the conversion factor. We use the conversion factor, and there we have it. We know there's 6.02 times 10 to the 23 electrons per mole. So we can cancel electrons. I'm going to get joules per mole, aren't we? And it's 1.312 times 10 to the 6 joules per mole. Then we need to convert the joules to kilojoules, and we can do that just by lowering it by 3 orders of magnitude. Evidence for energy levels and sublevels. The evidence for existence of energy levels Evidence for the existence of energy levels and sublevels comes from different types of experimental evidence. Here we can see atomic emission line spectra. We looked at that in the Atomic Structures 3 presentation. And underneath we have ionization energy data, and that's what we're going to look at. So what does ionization energy tell us about atoms? Let's have a look at these two. You can see that lithium has a higher first ionization energy, and so it will be harder to remove an electron because the electron is closer to the nucleus than in potassium, which has a lower ionization energy, so it's easier to remove the electron, and that's because the electron is farther away from the nucleus. So patterns of ionization energy can give indirect evidence about electron position. We know in lithium this electron is nearer the nucleus because this number is higher than this electron in potassium. Successive ionization energy values. In theory, each electron can be removed from an atom, one after another, starting with the outermost electron. The energy values for removing each electron are called successive ionization energies. And you can see the first ionization energy here. We've got a gaseous atom of magnesium being converted into an ion, a cation, and still in its gaseous form, releasing one electron. This has lost one electron. Then this here loses another electron for the second ionization energy. The third one, it loses another electron. Fourth, another. Fifth, another. Let's consider these ionization energy values. They're in kilojoules per mole. For magnesium, let's have a look here. They're obviously going up. So successive ionization energy values increase. What's the explanation? Well, when an electron is removed, the atom becomes positively charged. It takes more energy to remove the next electron from a positively charged particle. Let's consider these successive ionization energy values for magnesium. The increase in successive ionization energy values isn't equal. There's a large jump or gap between the second ionization energy and the third ionization energy. The electron configuration of magnesium is 282. So, there are 2 electrons in the outermost level. The third electron has a much higher ionization energy, so it must be closer to the nucleus than the first 2, and this makes sense with this model. This one and this one are further away than the next one that would need to be taken from this inner shell. Let's look at this example. The graph below shows the successive ionization energy values when the first 10 electrons are removed from an atom of a certain element. So you can see these 3 go gradually, then there's a jump, then these go gradually. Why is there a jump between the third and the fourth? Well, the fourth electron must be nearer the nucleus. It is closer to the nucleus and so more difficult to remove. It should stay there, just here. Which group of the periodic table would this element belong to? Group 13, that's right. Why is that? Well, imagine this one here, then this one here, and this one here were in, say, the third energy level, N3. This jump here starts at the second energy level. So these are all closer to the nucleus and so more difficult to remove because they are nearer. Draw an X to mark where you predict the ionization energy values to be for the 11th and 12th electron removed from the atom. This is where I think they are. Why is that? Well, think about it. This one here would be the first electron removed from the p orbital. So p6, p5, p4, p3, p2, p1. So that's all the p electrons removed. Now, S2 and S1 would be removed. So then we're going to have another gap here as you move to a lower energy level. This table shows the successive ionization values. I'm having trouble saying that. Ionization energy values when the first 5 electrons are removed from an atom of a certain element. In which group of the periodic table would this element belong? Well, group 1. And why is this? Straight away you can see the big gap here. So, little energy is required to remove the electron from the first ionization energy level, as it is furthest away from the nucleus, being at a higher energy level. The next 4 electrons require more energy to remove, as they are closer to the nucleus. There is a bit of a jump here between ionization energy 4 and ionization energy 5, because electrons being removed from a stable half-filled p orbital. More on that later. Let's consider the ionization energy values, the first ionization energy values moving across period 3. Let's have a look. So, there's something weird going on, isn't it? Let's explore more deeply. The general trend is the first ionization energy increases across a period as the atomic number increases. And this makes sense, because the valence electrons are all in n=3 for all elements in period 3. But the positive charge on the nucleus increases, so there's a stronger force of attraction between the outer electrons and the nucleus, so more energy is needed to remove the first electrons. But we saw something funny, didn't we? What about here and here? There seems to be some exceptions. We can see the exceptions to the rule as we move across a period on this graph a little clearer. We've got the first ionization energy on the y-axis, and we've got an increasing atomic number on the x-axis. And you can see the general trend goes up, and there's 2 exceptions. The exception here is from magnesium to aluminium. Magnesium has 3s2, and aluminium has 3s2, 3p1. So this is added sublevel. And this p sublevel is slightly further from the nucleus than the s sublevel. Therefore, the ionization energy decreases for atomic 13. This is evidence for sublevels. Hooray! Let's have a look at the other one. Phosphorus to sulfur. Phosphorus, 3s2, 3p3, going to, for sulfur, 3s2, 3p4. So there isn't an added sublevel this time. What's going on? Well, in sulfur, atomic number 16, there is pairing of electrons in one of the p orbitals. Repulsion between these electrons makes it somewhat easier to remove the first electron. We can think back to the bus metaphor. In sulfur, there would be 2 strangers sitting next to each other on a seat, and one of them would be happy to leave. In phosphorus, the 3 strangers all have their own seats. What are the key ideas we've learned? Well, successive ionization energy values for a given element are evidence for the existence of main energy levels in atoms. The pattern for the first ionization energy values of the elements across a period provide evidence for the S and P sublevels within one energy level. Splendid.